This is chapter 2. I believe the book calls it as dichotomous problem. Pretty much it is simply a test for proportion or small sample test or non-parametric test. Which we also call it as binomial test. Though we know what a binomial distribution is. Yes, no, right. You should know. Yeah, go ahead, enlighten us.
Well, it's a discrete distribution.
Okay.
And there's two outcomes, either a success or a failure. The events are independent, so the result from one doesn't affect the next one. And the probability of success stays constant.
Was it? It's making me proud. So, for something to be a binomial distribution, by something I mean a random variable. What does by mean? By means two of something. So where does that two come from? It comes from a success and a failure. So if it measures the number of successes, out of n independent trials. Independent in the sense the outcome of one trial cannot affect another. So if it happens, then we cannot use a binomial test. Now, what is a success event? Well, a success event could be any event of interest. It doesn't have to be a positive thing, even though success carries a positive connotation, doesn't have to be something positive. So success simply means an event of interest. So we have n independent trials, and P is known and P simply is the probability for success. So for us to use a binomial distribution, one has to know n and P. Without those two, we cannot evaluate because the probability mass function, that's my lowercase x, that is the formula to find the probability of each outcome. So if I have n independent trials, and if I want to measure the success or failure, let's just take a simple example, 7 students, and with each student, we'll just say the person had lunch or did not have lunch. So X is going to measure the number of students who had lunch. So having lunch would be a success event. That said, if you have 7 of them, so if you have 7 of them, what is the smallest number of successes that you can get? Do you follow the question?
No.
So 7 students, The success event is they had lunch or they did not. And X is going to measure the number of students who had lunch. If that is the case, what is the smallest value for X?
0.
0, right? Oftentimes the mistake that someone would make is X is equal to 1. X will start at 0. And what is the maximum value of X that we can have? 7 in our example. So generically speaking, it would be simply n. Now, do we really have to use this formula each and every time to evaluate in this class? No. I'm going to show you how to do this using a calculator, and I'll also show it using R. It is a programming language. You don't have to know programming in this class, but if you want to try it at home, you can. But you do have to know how to use the calculator for an example. So now that we have learned how to find the probabilities, we can go on to performing a binomial test. These probabilities that we found using the calculator play a significant role in, or not a significant role, the only way for you to come to a conclusion. Instead of getting into notation directly, I'm going to do it via example so that you learn it easily. And I looked at the book, so I'm going to use the notation that the book uses. So let's say I'm going to go with a lunch example. So the proportion of students who have lunch prior to a class at 1 p.m. is claimed to be 0.7. To verify the claim, a small sample is collected. I've got to make it random, and also we have too many people, so let me just look around. Okay, if you have anything black in your possession, then you will answer. Good. How many of you have black of some kind? You do. 1, 2, 3, 4, 5, 6, 7, 8, 9. Done. Too many. Well, we have to discard a few. I just want 7 people. So who wants to be discarded? You don't want, okay, so you two don't want to be. Okay, so you have one, so 3, 4, 5, 6, 7, right? Out of you 7 people, how many of you had lunch? 1, 2, okay. clearly that's way off from 0.7. So let's just, for the sake of it, change that to 0.3. And insert to be greater than 0.3. I want a good example. So we have 7 people, 2 out of 7. Greater than 0.3 might be a good one here. So we want to verify the claim. So I'm going to pick an alpha that I fixed to be 0.05. So use 0.05. And a binomial test to verify the claim. With me so far? So I'll give you a minute to write this down. So, what is the success event? We've been over this already. So having had lunch, so that would be the success event. Now, we don't have a probability of success. It is not stated in the problem, but we are performing a hypothesis test. So the probability will correspond to the null value that I have. What does the null, why do we call it the null value? If we go back to our definition of a hypothesis test, we did this last time with a large sample, I believe. Did we not do a hypothesis test for proportion last time? So we had P equals something, and I did a two-tailed test, P not equal to something. So that something is the value we claim. So P is equal to 0.3. The alternative in this case, though, it is not equal to, rather it is greater than. So P greater than 0.3. We can also write the null as less than or equal to, but I'm sticking to the notation that the book uses. This value, 0.3, is P naught. P naught simply means that would be your reference value. Relative to the reference is how we're going to verify the test. Now, we found the distribution, the probability distribution already. So the possible outcomes here are 0, 1, 2, 3, 4, 5, 6, and 7. Yes? And what are their probabilities? Did we write that down? I remember the very first one. It is 0.00022. Yes? What about the others?
Well, wouldn't it be different since we changed our point?
Oh, we changed the probability. Very good, Cleo. Got too excited there. In that case, go ahead and use your calculator with the new P and tell me what the probabilities are for this case. By all means, it's probably going to flip because we changed the success probability to a failure probability. So we want to find the probabilities. So as I mentioned earlier, it's just going to be flipped because we changed from 0.7 to 0.3. P became Q and Q became P. So it'll just be the reverse of the probabilities that we have. Regardless, The way to do it, first we enter 0 through 7 in list 1 and go over one that way. So let me clear the second list. And we are in list 2, hit the arrow, go up. And now you do second var and scroll down to binomial PDF, not CDF. You enter and type in n, p, x. N is 7. P in this case is 0.3 because that is the null value, comma, second 1. Good. Enter. So that's what we get. And if you go back and look at the previous list, it will just be the reverse of what we had. So earlier, we had 2.2 e raised -4 for x is equal to 0. Now it's just the reverse of what we had because 0.3 is simply 1 minus 0.7. We just flip things around. So now that we have the probabilities, let's go ahead and write them down. So 0.4 decimal places recommended. If you have scientific notation, make sure you retain scientific notation. Oh, it is 0.09724. For 5, it is 0.025. For 6, 0.00357. And lastly, for 7, it is 2.2 times 10 raised -4. Scientific notation, just keep it at this. So it's 2.187 times 10 raised -4, which is 2.2 times 10 raised -4. We have the probability values recorded. If you add all of them, it should add to the probabilities. If you add, it will sum to 1. And you can try this at home, it will sum to 1, yes.
So for all those probabilities, the binomial probability test, will they always be, the highest probabilities are always close to what you're testing for? Will that always be the case?
That's one. I designed it that way so that, you know, you can understand the test. Some cases are pretty obvious. If it is 2 out of 7 and I wanted to test it as greater than 0.9, clearly it's not going to happen, right? Because it's 2 out of 7, it's going to be a small probability close to 0. So I designed it this way so that we can understand the concept. That said, how did we come to a conclusion last time?
Hypothesis testing,
Come again?
a test.
We wanted to do a hypothesis test, and how did we do that?
We did a t-test.
We did a t-test, okay. Did we do a t-test or a proportion test?
Yeah, unless
But did we do population proportion or population mean?
population proportion.
Yeah, that's not a t-test, that's a z-test. So we want to come up with a rejection region. But before we get to that, let's see what the test statistic is. The test statistic is B. B simply is the number of successes. So in this case, it is 2. If, for instance, instead of giving 2 out of 7, had I said 16% of 7 people indicated that they had lunch, 16% of 7 will give you a decimal value. I always say round it to the nearest integer. People tend to round it up. I want to be cautious and I'll simply say round it to the nearest integer. Good. So in that case, it'll probably be 1.12. Yes. So 1.12, which is 1. Good. So some textbooks will stress, to count, so round up. I like to round it to the nearest integer. It's perfectly fine. So here we don't have that issue because 2 out of the 7 indicated they had lunch prior to class. So we know B is simply 2. This B is the test statistic for a binomial test. When we do a large sample approximation, I will do a large sample approximation also for this. It'll become a standardized test statistic. For now, this is an exact test. So simply the test statistic. And if the test statistic falls in the rejection region, we reject. And last time, we picked the rejection region using what? Yes, the critical value in this case, it's on the positive side, right up there. But then again, this is binomial, everything's going to be positive, but right inside. So how did we find that critical value? What did we use to find that critical value? It is given in the problem. That's my hint. So we have to make use of alpha. The book takes 2 different approaches in the sense, you can conveniently pick one and come up with an alpha value. But the way or the easier way for us to do this is to just keep it for 0.05. Definitely, I'm not going to hit 0.05, but I'm going to get closer and closer to 0.05. So here is the condition. The condition to reject null. So you would reject if the test statistic B is greater than or equal to B sub alpha. B sub alpha is our critical value. Good. Yes, no, maybe. Yes.
Why do you use B for the number of successes instead of X?
No, I'm just using the notation that the test statistic is denoted using the letter B. And B is X, the number of successes. So test statistic, critical value. Critical value is chosen in such a way that the probability, let's just call X greater than B sub alpha is equal to 0.05. So that is our condition. As I mentioned, I'm not going to get 0.05 in this case, yes. But I can keep on adding values. Greater than some number must result in 0.05. So if I set B sub alpha to be 7, anything past 7, the probability is 0. So the alpha that you can attain is 0.00022, correct? It's not 0.05. If I go one step, I can add those two values, and what do we get? It'll probably be 0.00379. Yes. And one more step over here, 0.000379 plus that value. And that would be 0.025 something. But I pick this, I'll end up getting 0.0974. That goes over 0.05. So I'm going to stop right there. Good. In other words, that value 5, because the probability greater than 5 or greater than 4 is 0.025 something. The sum of those. I'll write it this way. It's conventional. Less than or equal to B sub alpha would be equal to 0.25, which is alpha. Less than or equal to some value would mean greater than 1 minus the probability of greater than. So in our case, if I pick probability of x less than or equal to 4, that would be 1 minus the probability of x greater than 4. Yes? No, maybe. And we want to find the probability of x greater than 4. Sorry, did we stop at 4 or 5? Getting there. Give me 1 second. So 1 minus probability of x less than or equal to 4, complements of each other, right? Probability of x less than or equal to 4, 1 minus the probability of x greater than 4. Greater than 4 simply means greater than or equal to 5. Do you agree? Yes. So this would be probability of x greater than or equal to 5, which simply means I'm adding that value plus that value plus that value. So 0.025 plus 0.00357 plus 0.00022. And what do we get? What value to be? Oh, forgot to subtract when I flipped the greater than to less than. So it should be 1 minus point alpha. That will be 0.95. My bad. Because if 5% is on this side, 95% must lie that side. So B sub alpha corresponds to that probability. If you add all of them, what do we get? Definitely 0.0 something. 2.28. I'll just call it 0.0288. So the alpha that we chose is 0.05. But if I moved one step and picked 4 as the critical value, I am going to exceed 0.05, correct? So I would rather be below the 0.05. So I'm going to just say B alpha to be 5. Good. So if B sub alpha is equal to 5, I will reject. Excuse me, if the test statistic is greater than 5, I will reject. That's where my rejection region starts. Where is our test statistic? Our test statistic is 2. Did the test statistic fall in the rejection region? No. So our conclusion is do not reject. No. Good. If we do not reject null, we found evidence toward the null, but not the alternative. Do you agree? So we don't have enough evidence to support the alternative. I'm going to erase the top part. And in our problem, H1 is the claim. Do you agree? Yes. So since H1 is the claim, we don't have enough evidence to support the claim. Yes, no, maybe. So 2 out of 7, if you put it in the calculator, what do we get, the sample proportion? 0.28. Yes. So approximately 0.28. I think it's 0.2857. Approximately 0.28. It's very close to 3, but in this case, definitely less than 3. We can't find evidence toward the alternative. Does that make sense? I changed this to 0.3 because it'll become more trivial to do a test had I not changed that value. Another way to come to a conclusion, can that make sense? Is the p-value. Since this is a right-tail test, it is the probability above the test statistic. So in this case, the test statistic is 2. So I just call it greater than or equal to. So greater than or equal to 2. So you just have to add all of these probabilities. What do we get when we add those probabilities?
1.
1.
Is that what you said?
You start at 2 because that is B. We're adding all these probabilities. So 0.3177 plus 0.2269 plus 0.09724, 0.025 plus 0.00357, 0.0022, or 00.